Find the equation of the tangent plane to the elliptic paraboloid z equals x squared plus 4y squared at the point 4, negative 1, 20. So we have an elliptic paraboloid. So at the top here we have the cross section is elliptical. And we have some point on the paraboloid. And we want to find, at that point, we need a normal vector so that we can make our tangent plane. Because in order to find the equation of a plane, we need a point and a normal vector, a vector perpendicular to the plane. So now the way the theory goes is that we think of this surface as being a level surface of a function of three variables. So if we put the z on the other side, or equivalently the x squared plus 4y squared on the other side, we can think of this as z minus x squared minus 4y squared equals 0. And the left side of this equation is a function of three variables. So we have a function of three variables equal to a constant, and that makes the graph of this equation a level surface for the function g at the height 0. So what we know about level surfaces and perpendicularity is that the gradient of g will be perpendicular to the level surface. And that's how we're going to get our normal vector for the plane. It's going to be the gradient of this function g, not the gradient of this one here, but after we bring everything to one side so that we get a constant on the right side, then we could think of this equation as a level surface for this function. So we want the gradient of this new function here, a function of three variables. So the gradient of g is, by definition, the vector of partial derivatives g sub x, g sub y, g sub z. And in this case, g sub x is negative 2x, g sub y is negative 8y, and g sub z is 1. So at any point, this is our gradient vector, which means that the gradient vector at the point of interest for negative 120 is, plug in 4 here, you get negative 8. Plug in negative 1 here, and you get positive 8, and that's just the constant 1. So this is going to be our normal vector to the plane, which we usually call, when we're in the mode of finding equations of planes, we call that vector n. And so then you have a point on the plane. The point is x0, y0, z0. Just to review a little bit, finding the equation of a plane, and in this case that's the point 4, negative 120. And then a point xyz is in the plane. That's in the plane. If the vector from this point to xyz, that would be x minus 4, y minus negative 1, so y plus 1, and z minus 20. If this vector, 20, this vector should be perpendicular to n. And that means that the dot product should equal 0, and this will give us an equation. So we take the vector x minus 4, y plus 1, z minus 20, and we dot it with the gradient of the function of three variables, which is a level surface. That was the vector negative 8, 8, 1. Dot those together. And that should be 0, because these two vectors should be perpendicular to each other. this is a vector in the plane, and this is the normal to the plane. And that gives us the equation of a plane. Negative 8 times x minus 4 plus 8 times y plus 1 plus 1 times z minus 20 is equal to 0. And then with a little bit of rearranging, we could put it in the form ax plus by plus cz is equal to some number, d or something. So let's see if we can do that. Negative 8x plus 32 plus 8y plus 8 plus z minus 20 is equal to 0. So negative 8x plus 8y plus z is equal to negative 20. 32 and 8 are 40. 40 minus 20 is 20. And then we move it to the other side, so negative 20. And if we want to lead off with a positive, we could say 8x minus 8y minus z is equal to 20. Either way, we have a plane. We could also solve for z. Just put the z over here and the 20 over there. 8x minus 8y minus 20. So there's another form. This is the standard form here for the equation of a plane. So again, the main idea is that we think of the surface that we're given as being the level surface of a function of 3 variables. So we put all the variables on one side so that we'll get a 0 on the other side. And then this is a function of x, y, and z, a function of 3 variables. And then the gradient of that function will be perpendicular to this level surface. And that will give us our normal vector.